We have okay, good. We have 70 people online. Not bad. Good. Hello, Valerio.
Hello.
Let's start. Hello, everybody. Welcome to the Global Non-commutative Geometry Seminar today. We have speaker Dr. Valerio Proietti of East China Normal University. He will talk about non-commutative algebraic topology and hyperbolic dynamics. Please.
All right. Thank you for the introduction, and also thanks for the opportunity to speak here. So I have a little bit of a sore throat, so please excuse me if I have to interrupt every once in a while and clear my voice. Yeah, so before I forget, this is what I'm going to talk about today is joint work with Makoto Yamashita, who's in the audience. And it's mostly about two papers that are already on the archive, and we're working on a third one. And the point is a certain program of, let's say, discovering and computing algebraic invariants for a class of dynamical systems of hyperbolic nature. And so this, I would like this to sort of be inserted in a certain school of mathematics, which I guess starts with Stephen Smale, who started the study of sort of differentiable hyperbolic dynamics, and he coined a name for this system. They're called axiom systems. And after Smale, many people came, Ruel, Bowen, and they contributed to sort of like spreading the interest for these systems, and also, of course, for computing their algebraic invariants, kind of in a similar way as we do for topological spaces and just regular algebraic topology. So this is the outline for today. So first, I'd like to say a few more sort of precise things about what kind of system I want to consider. And I encourage you here to follow mostly the examples rather than the definitions, because I think the example really kind of describe that this class is very large, and all of the examples, so they draw connections to different fields of mathematics. I hope I can convince you these are into something, but they have a meaningful mathematical content. And also the sister algebras associated to these systems, since we're doing non-commutative geometry, they will also belong to a very wide spectrum. I'll say a few more words later. So we want to do some algebraic topology. So this will happen in part 2 and part 3. So part 2 will be mostly about sort of classical algebraic topology methods. So check homology and sheaf resolutions of sheaves. And part 3 is where sort of the non-commutative geometry enters the picture. So until part 2, there is basically no sister algebras and no K-theory. In part 3, we will basically exploit the triangulated structure of the KK category to do a bit of homotopy theory for these systems, and draw a connection between the K-theory and the cohomology theories that we studied in section 2. So okay, let's start with defining this system. So as I said, axiom A, this word originates with Stephen Smale. So before looking at the definition, you might have heard of the Smale's horseshoe map. So this is a very famous example due to him. So this is a diffeomorphism of the sphere, the S2, which has a fixed point in the North Pole, and then points flow from the North Pole to an area in the South Pole. And embedded in this South Pole area, there is a fractal, a counter set. And so the diffeomorphism restricted to this area acts like the shift of my type on two symbols, so the full two shift. So this was a very interesting example. Well, it is still now, but back then it was really one of the first examples where we could start with something really smooth and nice like a sphere, and a diffeomorphism over it, and then end up with some kind of very sort of combinatorial and fractal-like nature of this kind of dynamics that we have on the full two shift. So you start with a compact manifold and a diffeomorphism, as I said, and df would be the differential for me. So this goes on the tangent bundle. And so if I have a subset which is F invariant, I'll call it hyperbolic. If when I restrict the tangent bundle to it, it will split as a direct sum of two invariant df invariant distributions that are called the stable and unstable distributions. So this terminology comes from the fact that on the stable subbundle, I will see a contraction behavior, and on the unstable subbundle, there would be an expansion-like behavior. And then, as I just said, so there will be some Riemannian magic on M such that so df would be a contraction and on ES, and df on EU will be an expansion. So this is in symbol as it is. So there is this constant lambda which sort of controls the degree of contraction, and we have the splitting and the invariance, and then I have this bound here on the norm of df, which exactly says that it is a contraction. And then instead of saying I have an expansion, I say the inverse is a contraction here. Okay, so now we define what a hyperbolic set is. I want the set of non-wandering points to be hyperbolic. So omega f will be the set of non-wandering points. And so what this means is that for every, so a point is non-wandering if for every neighborhood u of that point, basically when I do f to some n of u, this will intersect u non-trivially. So there will be some point, maybe not my point, but some point close to there that sort of will come back. So now I have the two things I need. So when I am in this situation where the non-wandering points are compact and hyperbolic, which is what we just saw, and also the set of periodic points is dense in the non-wandering points, then I'll call this data an axiom A system. So as I was trying to illustrate also with the example of the horseshoe map, even though we have something smooth, the very interesting part of the dynamics actually occurs into a certain area, namely omega f, which is almost never a submanifold, and indeed very often it looks like something which is kind of a little bit pathological from the point of view of differential geometry. So because of this, it is useful to maybe move from this differentiable category to the topological one and sort of restrict ourselves to looking at the hyperbolic sets of axiom A systems and sort of forgetting the sort of like larger environment. And we will call these things Smale spaces. And these were so the rigorous definitions for. So I'm going to go through a series of examples here to show you, what kind of variety we can get. And for each of them, we will start from dimension 0 and work our way up to dimension 2. And for each of them, I like to sort of emphasize the local structure and the hyperbolic nature that we can see on these examples. So the first one should be familiar to people who are familiar with symbolic dynamics. So it's going to be the shifts of finite type. I call them here edge shifts because I present them as bi-infinite paths on a finite direct vertices, edges, initial vertex, and terminal vertex. And then a point in there would be this double infinite sequence, which is a path, namely, so the terminal vertex of some edge needs to match up with the initial vertex of the next edge. And there's this left shift map, which is a homeomorphism. So it is invertible because I'm considering sequences indexed by Z. So there is a metric which says that, so basically two infinite paths have distance less than 2 to the minus n minus 1 if they coincide on this central interval between minus n and n. So the edges belonging to this interval are the same, both for E and for F. And so if we look, if the distance is 1/2, that means that in particular, the edge at 0 is the same. So whenever the edge at 0 is the same, so they match up in this way, we can construct a new path by taking the past from the F path and the future from the E path. And so as you can see, this bracket map gives rise to a way of giving coordinates. And so this is going to be our local product structure. And here I'm talking about this constant. So roughly speaking, this is the distance, the maximum distance that 2 points can have such that I can trivialize this product structure so that this bracket map is well defined. So just to be more concrete, for example, if I have a graph, very simple one with one vertex and 2 loops, So basically an infinite path can go through a time 0. It can either go through A or through B. And therefore this space is this joint union of two clopens. So the path whose central edge at 0 goes through A and the other one's for B. And the bracket map is well defined on each of these. And so it gives us a presentation as a with a product structure here as these two squares. So where each path belonging on a square can be determined by basically describing the coordinate of the past and the one of the future. So in this picture, it is fairly easy to see what the hyperbolic assumption means. So in this picture here, we have two paths, Z and Y. They lie on the same vertical line. So that means that their future is the same. So the first edge is B, then the second edge is E2, then we have E3. But you can see their paths are different. They're labeled Z and Y. Now, because the distance decreases when the paths agree on larger and larger central intervals, when I shift these two paths to the left, well, first of all, we see that the -1 path, this -1 edge will be A, and the 0 edge will be B, because on the left picture we have B is the 1 edge. So now they get shifted, they get sent into the other clopens, the one for E0 equal B, and they agree on this larger interval because now at -1 time they both are equal to A. And therefore, because of the way the distance works, we see that the distance has contracted. So they're getting closer. If the two paths lied on a horizontal line, then we would have expansion. So you can see here that the local structure, so that would be the topological class of the X and Y axis is counter set times counter set. And so this is an example from symbolic dynamics. Now, this is an example which really is presented as an axiom A system, not just as a Smale space. So before looking at the formulas here, I want to show you the picture. So you start with the solid torus, the red one on the left. And then what you do is you stretch it in the longitudinal direction, and then you contract the meridional disks. And then you put it inside itself. And then you keep repeating this process. So here already you start seeing the hyperbolic nature once again, because one direction gets stretched and the other direction, the disks, they get contracted. Okay, so what happens is that I want to find something which is invariant, on which my map is bijective. So what I need to do, I need to keep repeating this process and then considering the nested intersection of all these iterated images of my original map. And then the map restricted to this nested intersection will finally be a homeomorphism, and that will be the Smale space I want to consider. So as you can see, the disks are getting somehow fragmented, and eventually they will become counter sets, while in the longitudinal direction, I retain, even in the limit, this line. So the local structure will be something like counter set times R. And so the unstable part is R, and the stable part is counter set. So in formulas, yes, you have the closed unit disk D2 and S1, that will be the solid torus. And then I have this map phi, and the one was in the picture can be described through the simple formula here. And as I said, basically you have the stretching in the longitudinal map, this torus around itself, and without self intersections. That's what we're doing. So yeah, so this solid torus and phi, this is an axiom A system, and as I said, lambda, so the hyperbolic set will be this nested intersection. And then if we want to present it in a nicer way, we can actually see, well, okay, a nested intersection is in a projective limit. So there will be another projective limit and a system which is conjugate to lambda, and that will be the circle and the squaring map on the circle. So we consider this inverse limit space, and the map F would be the map that squares all the coordinates. And this is invertible because we can shift, because of the way the projective limit is defined. By shifting, we can recover the image. So as I said, the local structure here is R times Cantor. So a third example, which has maybe a number theoretic flavor of some sort, is coming from the p-adic numbers. So if P and Q are 2 primes and I assume Q is bigger than P, I can consider QP times R times QQ and define this map there, which is the multiplication by Q over P on each coordinate. And so you can see that on QP, P inverse expands and Q is an isometry. On R, Q mod P expands simply because Q is bigger than P. And on QQ dually, we have the P inverse is an isometry and Q contracts. So the problem with this space is that it is not compact, but there is an invariant lattice, which is the integers and then adjoined with all the numbers whose denominators are powers of PQ. And so we can mod out by this lattice and the local structure is the same. And now we get a compact set. And so here the unstable direction is given by reals times Cantor, and the stable direction is given by Cantor. So we have Cantor space. So this is the local product structure. So one more example coming from maybe group theory and self-similar group actions. So here there is some jargon that's kind of technical to self-similar group actions. It's not too important for us. So I'll be brief on these conditions. So we have a group acting on a finite alphabet A, and we can let it act on the, so we can consider a tree given by basically constructing words on this letter, on these letters. And then the group will act on the boundary of this tree, which I represent here as the infinite sequences open-ended on the right. And so I have some conditions on these actions. So self-replicating, contracting, irregular. So regular means that the fixed point sets should be open and also they're closed. Self-replicating is a technical condition. Basically, in order to say that two self-similar groups, so which is this dot of G and A, are equivalent, we define a certain bimodular associated to it, and there is a right action there. And if of the group, and if this action is transitive, we call the data self-replicating. And then contracting means that there is a certain subgroup N in G, which is finite. And well, okay, very roughly speaking, when the group acts on a word which is long enough, the action will involve elements from this subgroup N, which is called the nucleus. So this is what contracting means. In particular, there is this N subgroup of G, which is kind of important. So we can construct a space here, and it's going to be called X. It's the quotient of AZ. So now a sequence is open-ended on left and right by this asymptotic equivalence relation, which says that so X and Y, these double infinite sequences, are equivalent if there exists this sequence Gn in N, such that when I add, so I add Gn on Xn, I get Yn and then Gn plus 1. So the way to read this equality is that, well, so Xn, you can think of Xn as like a letter and then a continuing, so the rest of a word. And so Gn will act on this letter and I will get a new letter called Yn. And then on the rest of the subword, the action is given by Gn plus 1. So this is what this equality means. So the shift map on this X gives us Mail space. So we get this example from self-similar group actions. In particular, there is a very interesting sort of, I guess, special case of this example coming from complex dynamics. So if I take a rational function and I let it act on the Riemann sphere, so the function must be post-critically finite, which means that the orbits of critical points, the forward orbits are finite, and it must be a hyperbolic function of points where the derivative is 0, must converge to an attracting cycle, so a subperiodic cycle. Then I can consider what's called the iterated monodromy group of F. So basically, if I remove from the Riemann sphere the union of the definite forward orbits of these critical points. So the complementary of this, I can restrict F to this, and I will get a partial self-covering. So in particular, there is the monodromy action associated to a covering, and this is an iterated one because I need to mod out by a certain kernel that I don't have time to define here. But the interesting thing about this is that now you get this self-similar group action, and you go through this construction of the space X, and you get something whose local structure looks like the Julia set of F and the counter space. And so the Julia set is one of the sets that appears in complex dynamics. It's the complementary of the Fatou set. And it's basically those values such that arbitrary perturbations of these values basically give rise to a drastic change in the sequence of iterated applications of my function. So it's also defined as the closure of the periodic repelling points. Okay, so we have this very sort of interesting sort of the connection to fractals as well. Okay, so finally, my last example is a two-dimensional one, maybe slightly more geometric. And so this example will give rise to the, so as in sister algebra world, will give rise to the rational rotation algebra. So here I get a hyperbolic matrix. So it has determinant 1, and it's diagonalizable with eigenvalues 1 bigger than 1 and 1 smaller than 1. And so here B is the base that I need to use to diagonalize, and phi is the golden section. So because my action descends to, so respect Z2, the lattice descends to an action of the torus. So I have a hyperbolic toral automorphism. These are examples of Anosov diffeomorphisms. So Anosov is another mathematician who studied these systems very much. So this is a Mail space, provided my constant, the constant that sort of regulates the local structure, is chosen small enough so that I don't, so basically if I consider a fundamental domain for R2 mod Z2, the edge of my ball of radius epsilon is away from the borders of this fundamental domain. And of course, this action, so this example can be generalized to any lattice preserving hyperbolic linear map. And so you can see here the local structure is given by the lines that go through the eigenvectors of A. And so I get R times R. And so, yes, so this is the picture you should have in mind. So this yellowish area is what my epsilon, my distance is constraining. And you can see I'm away from the borders. So in that area, I can choose coordinates given by the directions of the eigenvectors. Okay, so before moving to this part, I showed you now 5 examples. I hope I convinced you that these are interesting things to consider. So because they come in a very wide variety. As I wanted to say, so later we will consider sister algebras, and I want to just emphasize right now that also the sister algebras that we get, also they belong to a very wide spectrum. So we can get AF algebras, Kunz-Krieger algebras, then we can get Bunsteden's algebras, irrational rotation algebras, purely infinite algebras. So we have this wide class of sister algebras which we can view in a unified way, which somehow underlying this view, there is a geometric dynamical understanding. And this is useful for computations because, of course, a geometric picture is very useful usually in computing invariants. Okay, so having presented all these examples, I want to pass to section 2, where we will look at a homology theory for these systems. So this has been defined by Ian Putnam. And so I want to motivate it here by looking at check homology and drawing a certain analogy. And later on, I want to identify this theory with the groupoid homology in the sense of equivariant sheaves. So it's good to introduce sheaves from the beginning in some sense. So if, for example, I have X is a complex Hasse space, which is the support of a Smith space anyway, and I have a sheaf over X, say 1 billion groups. So the recipe for computing check homology, or maybe rather I should say, the reason why maybe check homology computes sheaf cohomology, it's because it works in the following way. So we pick a good open cover U of X, and we know what good means. And then there is this resolution. So we just pick this natural surjective map onto X given by the disjoint union of all these opens. And then we consider the multiplicities which make up the check cochain complex. And at the level of sheaves, what we are doing here really is we take the functor of the sheaf. And so these are actually adjoint to each other and they form a monad. So in particular, this phi star phi inverse F, this inherits a cosimplicit structure augmented over F, which is our original sheaf. So when we pass from a cosimplicit structure to a chain complex, we get an acyclic resolution of sheaves. And it is acyclic because the open cover we picked was good. So in particular, you know, the intersections of all these opens are contractible spaces. And so, okay, we got a cochain complex, as I said, by applying some functor, which in the case of sheaf homology is the global section functor. So we look at these steps and we want to replicate them in the case of Smale spaces. I mean, as closer as we get, as we can get. So here, because I explained Smale spaces are obtained as a double foliation, so there's a stable one and an unstable one, it is reasonable to expect that instead of a chain complex, a linear one, we get a double complex. So I want to avoid this because notation sort of explodes and it's better to just present maybe a just slightly simpler case. So I restrict myself to the class of Smale spaces whose stable coordinate is totally disconnected. So this rules out the last example I showed, the one of the torus, but all the other ones are good. So it's not that this construction doesn't work, it's just that it's easier to present this one because there's less notation. It has a clear sort of similarity to check homology. So instead of a good open cover, we pick a good partition P of X, and that's a Markov partition. So that's something that people in symbolic dynamics understand very well. So given a Markov partition, we can construct a shift on the partition and either not to be a shift of finite type. And so there is this map phi, which is a surjective map, and it's going to be also equivariant. And so as I said, domains, you see sigma p is a shift of finite type. So this map is a resolution in the sense that it has this specific quality that it is bijective on the local stable coordinates. So I'll say a few more things in the next slide about this. Okay, so then we need to deal with multiplicities. So as we did for check cohomology. So there we had this sheaf construction. So here, for the moment, we go a little bit more hands-on and we just consider basically the fiber product of our shift of finite type sigma p over itself, over the map phi. And so, you know, sigma n of phi will be just an n+1 tuple of paths on sigma p, which all map down onto x on the same element. Okay, so this is a simplicial structure. Clearly, you know, we have projections down from sigma n to sigma n-1. So we're getting closer. And now, how do we get a chain complex? So now we need a functor to abelian groups. So this is what's lacking at the moment. So before I answer this question, I want to say a few more things on what this resolution and this bijectivity on local stable set looks like. So I have an example here on top. Let's look at the definition before that. So equivariant surjection of Smale spaces is called S bijective if it is a local homeomorphism when I restrict it on the stable sects. So, you know, locally I have this product structure. So I can restrict my map on this open where I have this trivialization, and I ask that on the stable coordinates, I get a local homeomorphism. So an example of that, we can give it using the examples that I showed before. So I gave an example of a full two shift. This was the shift of finite type arising from the graph with two loops. And also I gave the example of the dyadic solenoid. So this was the torus, which was sort of getting stretched and getting wrapped around itself. So the hyperbolic set for that axiom A system is called the dyadic solenoid. So it is the inverse limit of the squaring map on the circle. So this phi, so there is a Markov partition for X, and it gives rise to the full two shift. So I'm not going to write the Markov partition, but I can tell you exactly what the S bijection looks like. So there is this formula. The way to understand this formula is it's actually not that hard. So X is an inverse limit of circles. So if we take one circle, we can view it as the exponential of the unit interval. So first we code the unit interval via the binary expansion of points in the unit interval. And that's what you see in this summation inside. And then we exponentiate this coding to get a coding of the circle. Once you get this down, since both sigma 2 and X can be expressed, and that's where somehow you need to pay attention to the indices and the subscripts here. But basically, this is what's happening. Okay, so when I apply fiber products over phi, I get, as I said, this nice simplicial structure. So this is a bunch of shifts of finite type, all mapping down, and then augmented over the original space, which is the one I want to compute the invariant of, which I call X. As I said, we need a functor which sends this simplicial structure to abelian groups so that we get a chain complex. Now, I said before that shifts of finite types can be presented as edge shifts. So that means that they can be presented as the paths on a graph. So each of these sigma n's is going to be conjugate to some edge shift sigma gn. So the graph for sigma n, I'll call it gn. And then I let Vn be the number of vertices of Gn, and An will be the adjacency matrix of Gn. So the adjacency matrix tells me, so given two vertices, how many edges go through them. Okay, so then there is this invariant. It's an abelian group. It's been defined by Krieger for the shift of finite type. And it is a stationary inductive limit over the free abelian group generated by the vertices of my graph. And then I have the map A, so viewed as a linear map, the adjacency matrix acting on it. Now note that the limit is not over n. N is fixed. So sigma n is one of these shifts inside this simplicial structure. And the limit is actually, so I wrote k there just to emphasize that the limit is not over n is fixed. So this is a stationary inductive limit. So the construction of the dimension group is actually functorial with respect to S bijections. So once we have that, I can apply this functor ds to my sigma dot, get a simplicial group, hence a chain complex, and get a homology of that and define that to be the homology of X. Of course, you need to do some things. For example, you need to check that this definition doesn't depend on phi. And so this is mainly due to Ian Putnam. There are different complexes that one can associate to this, a smaller one and a bigger one. And so basically joining papers from myself and Ian Putnam, we can say that all of the different constructions that we can make give rise to this homology, which is well defined. And so this is our definition. And so our job from now on is to conclude this second section, is to identify this homology theory that I just defined with something maybe more familiar, which is has a more maybe algebraic nature, which would be the homology of étale groupoids in the sense of equivariant sheaves. So this definition of the homology given by Putnam is quite beautiful because it really it defines intrinsically using dynamics and using symbolic dynamics, but it has a drawback that it is very hard to come up with long exact sequences, for example, and just like machinery for computations, because the construction is very ad hoc. And so maybe by shifting to a different definition from the point of view of dynamic systems, we might gain as advantages long exact sequence or other kind of machinery. So because groupoids will play a role, I will introduce groupoids, and the sister algebras, of course, will be sister algebras of these groupoids. So there are two equivalence relations. one is dual to the other in the sense that one is obtained by inverting the map on the dynamical system. So I will focus on one. I will focus on the unstable equivalence relation, and x and y in X, these are 2 points in my small space, they are unstably equivalent if the distance, basically, if I look at the past of these 2 points, the distance of these respective points goes to 0. So in symbols, I apply f, the iterated images of x and y through f, their distance will go to 0. So this equivalence relation is a locally compact house of groupoid and has a Haar system. And it can be made up to Moridi equivalence into an étale groupoid using a very, I guess, a very familiar procedure for people in non-commutative geometry, which comes from probably foliations. What we do is we reduce the groupoid, so we reduce the unit space of the groupoid to a certain transversal. And because the situation here is quite geometric, I'm considering the unstable equivalence relation. Therefore, it is very natural that the stable orbits will be transversal to the unstable arrows. So to speak. And indeed, if we orbit, and maybe we have some mixing hypothesis on the system, and re-topologize, giving a certain topology, a certain étale topology, we obtain a Moridi equivalent groupoid, which I will still denote RUXF. So this is just for convenience for this talk. And the sister algebra of it will be the sister algebra of the small space in this case. And this groupoid is amenable. So the norm in which I closed the convolution algebra, it doesn't matter. So before we move on to identifying this theory, let me make 2 observations which tie up the dimension group construction, which is our functor to abelian group, with the theory of operator K theory and sister algebras. So first of all, if we apply this unstable equivalence relation construction to a shift of finite type, we get an AF groupoid and an AF sister algebra. And therefore, its K theory will be a dimension group. In particular, it's going to be exactly Krieger's dimension group. And so on K0, of course, and K1 is going to be 0. So, oops, something, sorry, I did something. Okay, we're back here. So the first observation is that the even K theory of the unstable sister algebra associated to a shift of finite type recovers the Krieger invariant, which is our recipe to get a chain complex. The second observation is that if I get an S bijection between 2 small spaces, so for example, here Y could be a shift of finite type and X would be the space that we want to compute the homology of. If we look at what phi induces at the level of groupoids, it will induce an open inclusion. So this allows us to view RUY inside RUX as an open groupoid, subgroupoid. All right, so with this in our hands, let's move to equivariant sheaves and groupoid homology. So a G equivariant sheaf, so G is a groupoid over X, is a sheaf F over X together with an isomorphism of sheaves between the pullback sheaf over the source map and the pullback over the range map of the sheaf. So if you think of a sheaf as people in analysis do, so as a étalé space associated to a sheaf, that means it's a space with a surjective local homomorphism over X, then a G equivariant sheaf is just asking that this étalé space has a G action, and the anchor for this action is given exactly by this local homomorphism down onto X. Even though we don't need it, I want to emphasize that because we are working with groupoids whose unit space is the stable orbit of a small space, and we are under this assumption that the small space is stably disconnected, these groupoids are ample, and so G sheaves over, so ample groupoids can be also thought as unitary CCGZ modules. So this unitary means that there is a certain factorization property. And the correspondence between unitary modules and G sheaves over ample groupoids is given as it's written here. We can take sections of the sheaves by considering this multiplication of the compactly supported functions on a certain open with values over the integers and multiplying that with the left module structure of M. Now we will consider resolutions of sheaves, and the important notion here is the one of C-soft sheaves. So this comes from, it's the familiar, I guess, definition which we see, for example, in algebraic geometry or well, I guess when we study sheaf cohomology. So sheaf F is soft if for any closed subspace K and Y and section over K, there is a global section whose restriction to K match up with the section I was given. And so because we are under this ample situation, this is equivalent to C softness, which is where K is compact instead of closed. All right, so under a certain assumption of sort of finite cohomological dimension that we definitely have over the unit space, we can take a C-soft resolution of F, and our assumption on the so the cohomology is bounded tells us that the resolution ends on the right, so it's not open-ended. And this is, of course, we can do it. So how do we obtain this resolution? Well, we can truncate the canonical flat B Godemar resolution, or even more abstractly, I mean, so we just know that the category of G sheaves has enough injectives and we can truncate. And I guess in a sense, the Godemar way is a way of showing that we have enough injectives. Okay, so then by inverting the bounded below chain complex given by this resolution of sheaves, chain complex in sheaves, and the groupoid homology of G with values in this sheaf F, this G sheaf F, is the so-called hyperhomology of G with values in this chain complex of sheaves. So what is the hyperhomology? So it's the homology of a total complex of a certain double complex. So the two directions in this double complex are given, well, one direction is given exactly by S minus dot. So there would be a direction, one line for S0, one line for S1, and one line for S2, and so forth. So that would be one direction. The other direction is obtained by expanding G via the bar resolution. So the canonical bar resolution that we have for groups, there is of course a natural extension of that for groupoids. And so for a fixed C-soft sheaf F, so this could be one of my SIs, the other direction will look like this chain complex below, where I take compactly supported sections over sort of this Gn. So these are n tuple, so arrows whose range and source match up with values in a certain pullback sheaf, which is just my sheaf, but then I pull it back using this map Tn, which is just a projection onto the range of the first arrow. So this is just so that things match up. And then I have these differentials, so these maps going down, and these are induced by the nerve structure, as I was saying, of G, so by the bar resolution. And these are covariant because I'm considering compactly supported sections, and these face maps of G are étale. So let me show you what I mean by this. So yeah, so we have this bar resolution, there is this nerve of G, the usual one, and we get these face maps, and these face maps induce on the compactly supported sections maps which go in the same direction because of their étale. And okay, the face maps are the usual ones. So the first one forgets the first arrow, the last one forgets the last arrow, and then in the middle, I just compose two arrows. And then in the case where I have n equal 1, the arrows are given by range and source. The general is not important for us, but it's given by insertions of units. Okay, so now how does this homology of groupoid relate to what we have here? Well, we consider a shift of finite type and the unstable equivalence relation over it. It is a groupoid. And then we have the sheaf, this locally constant sheaf of integers. So the homology of that in degree 0 is actually our invariant, so the Krieger invariant. This should not surprise anybody, I guess. And in higher degrees, we get 0. So it's the same as the K-theory, as you can see. Okay, so now that we are in this new context, we can really try to mimic the Czech homology construction. Well, I guess the dual construction of that. And this will be our sketch of proof. So I will be brief on this. So if I have a F and RUXF sheaf, so F as an action of my unstable groupoid of X, I can construct this resolution, this sigma mapping down on X. Very good. So this is the starting point of the definition of the homology that we had before. So this is my resolution in terms of spaces. It's an S bijective map. Now we have this adjoint situation because between the category of sheaves equivalent over sigma and the one equivalent over X. So it's given by the pullback on one functor, and then the shriek sort of push forward on the other this is the other functor. So we see that together with the push forward and the direct inverse image functor, these functors are 4 of the so-called 6 operations of Grothendieck, which are, I guess, so they are very used, of course, for example, in algebraic geometry, and there are several adjunctions which relate these 6 operations. And in a sense, so in a different setting, that's exactly what we are using here. So there would be some hypotheses, for example, the fact that I have this S bijectivity, which will allow me to say that I have an adjunction. So there would be some underlying assumptions that I'm sort of like sweeping under the rug. So what I do now is that I do the dual construction of the Czech construction. So I have a pullback and then this shriek functor. And this will give me not a co-simplicial thing, but a simplicial thing. Because this composition of functor is so it's an endofunctor on sheaves over X, and it is actually now a comonad. So this is now a simplicial sheaf in the category of sheaves over X augmented over F. And so what we want to say is that this is a resolution of F, of course. And then we want to compute the hyperhomology. Also note that for the case we're interested in, so when I pull back the locally constant integers, so what do we do? Well, okay, our chain complex is given by the dimension groups of the sigma n's. So sigma n is this iterated fiber product of sigma over X over itself. So what we need to do is we need to somehow relate the homology of this sigma n's with the and their sheaves and with the homology of X. And what we use is this proposition which sort of comes to our rescue here. So it's a general proposition. If I get some sheaf, say F, it's an RU sigma sheaf. Now sigma maps down onto X, so I can push forward in this shriek sense the sheaf, and I get a new sheaf over X, so RUX. Now what happens is that the homology of these is of these two sheaves over the respective groupoids, they are isomorphic. Moreover, if I have a fiber product, and I can consider the sheaves that I construct by using the my functors in the two different ways, I get this isomorphism. Now we are interested in the case where, of course, y equals z equals sigma, and P and Q are the projection maps, and the maps pi and rho are the same map, and they're the map phi that I've been talking about. So if we look at what this proposition means for the case of iterated fiber product, where, for example, you can do the case of sigma 1, where I only have 2 copies of sigma, you can see that what it means is that so the zero homology of the groupoid at the level sigma n is the zero homology of X, and then I have to replace the sheaf by my construction, by my comonad applied n times to the sheaf of integers, which is the one I want to resolve. So because of this, we can get this identification of chain complexes. And this is why we get this identification of homologies. There are some details here to check, but basically this is the idea of proof. So the homology of main spaces in the sense of Putnam, defined through symbolic dynamics, is the entire Groupoid homology of its associated equivalence relation in the sense of equivalent sheaves. So I was talking about the advantages of this identification and the fact that there is no machinery for Putnam's definition. So here are a few corollaries that you get for free once you get this identification. You get the Kunet formula, a general one, and then you also get duality. So what I mean by this is some kind of generalization of Poincare duality. And here I have a caveat. So duality in some cases. So when the groupoid is such that it is more equivalent to some kind of transformation groupoid, in which I know that the group associated to this transformation has duality, then I get duality here as well. Okay, so I have maybe 5 more minutes, and this is the part that I guess we're more familiar with, sister algebras and K-theory. So as I said, so far we have dealt with very classical algebraic topology methods, so this check homology and resolutions of sheaves. Now we want to do homotopy theory in a non-commutative sense, and we will use KK theory. So in case you're not familiar with KK theory and you're wondering, or maybe you're familiar with the Kasparov definition of KK theory, so the concrete one, you're wondering, okay, so how do I do abstract homotopy theory in KK theory? This theorem should sort of give you an idea. Indeed, if I consider the KK category, this actually embeds into the stable homotopy category. And so in particular, there is this functor. So a certain sister algebra A gets sent to a certain spectrum Ka in the stable homotopy category. And the nth homotopy group of the spectrum is exactly the nth K group of A. If I specialize this functor on the subcategory of sister algebras which satisfy the UCT and also satisfies Spanner-White duality, so Poincare duality as it was previously called, this functor becomes full and faithful. And so in particular, the sister algebras will be realized as perfect KU modules. So what this means is that they are compact objects in the category of module spectra. And in particular, they are finite spectra. So for example, if you want to say that a dualizable object has finitely generated K-theory groups, you can use this functor and then say, well, okay, finite spectra have finitely generated homotopy groups. This is known in algebraic topology. So that's how you get that. So what this does is it encourages us to consider Smith space in the setting of KK theory. So what we do is we pick a Smith space X and its equivalence relation RU. I'm calling it G now because it's going to be easier. Now C0X is the sister algebra associated to X, and it's a G algebra because G acts on X. I have again this S bijective resolution sigma to X. And then, as I said before, this was my second observation. I get an RU sigma will be called H, and RUX will be called G. So I will view H inside G as an open subgroupoid. Now, again, as it was for sheaves, I get this adjoint situation. So what I can do with this, I can start doing relative homological algebra. So I can define weakly contractible objects and projective objects. So a weakly contractible object is something in KKG such that after restriction to KKH becomes contractible, and a projective object will be a retract of an induced object. So I get a triangulated structure inherited from the stable homotopy category, and therefore I can perform localization with respect to the homological idea of weakly contractible objects. So what this means roughly is that I take some algebra, some G algebra, and I start removing contractible pieces from that algebra until I get a certain nice approximation. So this is roughly how it works. So I fix a projective resolution of A. This exists by using basically, well, either by using the bar resolution or by inducing again from H. And then I get this diagram. So A here is C0X, but it could be any G algebra. And here I get my resolution. And so I embed each morphism in the resolution in a certain triangle. I can do this because of the axiom of triangulated categories. And then I get these maps pi1, pi2, pi3 because these p0, p1, p2, they are projective. So I can construct this tower. So by looking at the structure of this tower, we can get an exact couple and therefore a spectral sequence. And I just want to discuss where does the spectral sequence converge? Well, it converges to exactly the object I get if I start removing the objects Ni, removing in a certain sense, I start removing those objects from A. So the object I get is called PC0x. And in particular, it is the image of C0x under the adjoint of the inclusion of the projective objects inside KKG. And I get this exact triangle here. So I get a map from PC0x from my approximation to the original object. And it is known that, okay, now I apply descent. So my G was RUXF. So here I get the sister algebra I'm interested in. And here I get this other sister algebra, which is known to be the source of the Dirac morphism. So this is the approach used in the Baum-Kohn conjecture. Now, because G is amenable, this map is actually an isomorphism. So the convergence here is not to PC0x, but actually to C0x itself, because these two objects are equivalent. And therefore, I get to my conclusion here that I get with the exact couple that I get from this tower, I construct this spectral sequence. And on the second sheet, I get a homology theory, which is given by the chain complex of K groups of P cross G, where P dot is my projective resolution, and it's converging to the K theory of the sister algebra I want. Now, one last thing, what is this homology theory? So can I identify the homology of Smale spaces with the comonadic theory here that I get? So I call it comonadic because induction restriction form a comonad. And so the answer is yes. And so, for example, if you look at P0, it will look something like C0G cross H. In particular, when I now descend, I had a left action of G, and this will get me C star of H. Now remember, H or RU of sigma, and the K theory of RU of sigma, this was my first observation, is the dimension group ds sigma. So at least in the first step, I get the right chain complex, and then I can keep going. So the conclusion is this. Now I rewrite the spectral sequence I had before. And now on the second sheet, I see the homology of Smale spaces. And it's converging to the K theory of the sister algebra I want. Now, because the homology is defined through dimension groups, which are finely generated, as a corollary here, for example, I get the finiteness of the rank of the K groups. This is because I have this comparison to the homology groups, where I already have this finite rank. So this is another sort of like advantage of drawing this sort of comparison using more familiar homology and homotopy theory invariants. Okay, so that's all I wanted to say. Thank you very much for your attention.
Okay, thank you, Valerio, for the wonderful lecture. Are there any questions or comments from the audience? Why is the sister algebra is amenable?
Sorry, my connection skipped. So can you repeat what you said?
Why is the sister algebra amenable? It's in the previous page or the last?
Oh yes. Oh yeah. So this is because of the. I mean, okay. So really, it's really because of the hyperbolicity. So for example, so you can look at the. So because you have this hyperbolicity, you can study this structure. This has been studied, for example, by Claire Antanaran de la Roche, and so you can see that. So she, for example, had a result where if you now cross G with Z, which is the action given, so basically the automorphism given by there, this groupoid will give rise to a purely infinite sister algebra, for example. This is also due to the hyperbolicity. And then there is a paper by Putnam and Spielberg where, again, they studied basically this, well, so they studied this structure here. And well, so basically they are able to prove that the groupoid is amenable. So I don't remember the details, but it really comes down to the fact that it goes back really to the nature of the dynamical system, so the hyperbolicity.
Okay. Makoto, please, you may have any question?
Sorry, me?
Yes, please.
No.
Makoto knows this very well, I guess, so he doesn't have a question.
Only people knows well can raise some questions, I think.
That's true. That's true as well.
Well, Makoto, what is clear border? Clear border is in the audience. Professor Claire.
Claire de Boer.
Claire de Boer, sorry, Claire de Boer. Kabara, what is in the desk of the office? Please look back your office. There's some toy or something.